Audio Jungle. Audio Jungle.
Right. So this is what nozzle. Okay. So what is the function of nozzle? The function of nozzle is what? To convert gas potential energy, or better to say pressure energy and thermal energy into kinetic energy. Okay, gas velocity, and that is necessary for the generation of thrust. Okay, so this nozzle basically used to convert all pressure energy available here into kinetic energy. Okay, and that is required for generation of thrust. Required for the generation of thrust. All right. Now the propelling nozzle to refer the component in which the working fluid is expanded to give a high velocity jet. Okay, and as I told you, two components, which is the diffuser and nozzle, are the static component of the engine. All right, just like a turbine and compressor and turbine was both were the rotatory component, or you can say mechanical component. But here it is nozzle and diffuser both are the only static component. So how this conversion, I mean potential energy to kinetic energy, how it is possible? So it is possible by the geometrical shape of the nozzle. Okay, by geometrical shape of the nozzle. So uh, based on this geometry, we have a two type of nozzle, that is convergent nozzle, and one is what, convergent and divergent nozzle. Okay, so the function of, basically the function of nozzle you have seen here. What is the function? In short, I will write function of nozzles. So the functions are, I'm just going to write in point. So the function are okay. So it is nothing but accelerate, accelerate the flow, accelerate the flow to high velocity with minimum pressure loss. Okay, match, that design should be like match exit and atmospheric pressure as closely as desired, called optimum condition. Okay, it will permit operation of afterburner. Afterburner is basically one thrust augmenting device. Okay, So where you will install afterburner whenever it is required. So you will install afterburner in nozzle only. Okay, in constant area of the nozzle somewhere you have to install. So permit afterburner operation without affecting main engine operation, or only I am writing here permit operation of afterburner. That's all. Okay. Now allow for thrust vectoring, allow for thrust vectoring. Okay. The very important last, suppress jet noise, suppress jet noise. Okay. And and infrared radiation. So these are the few important points here I have mentioned. It is under function of the nozzles. Okay. So these few points you need to remember. Right. Now types of nozzle. So we have basically two types of the nozzle here. Okay. And in aerodynamics already I have discussed, so you are aware with this. First one is the convergent nozzle. Second one is the convergent divergent nozzle. So already I have discussed about convergent nozzle and CD nozzle, convergent divergent, both I have discussed. Okay. So here, see, this is the convergent nozzle. Alright. So if the flow is the subsonic flow, okay, then convergent nozzle is what suitable here. So if m is what less than 1, then maximum m is equal to 1, possible maximum I am saying, okay, Mach number. So this is what convergent nozzle. So this is called subsonic nozzle. So at the exit, maximum Mach number possible is what, 1, not more than that. But so it is what, subsonic. All right. Now we'll go for the supersonic. So supersonic nozzle we have convergent and so already I have given the derivation and all discussion we had done, so I am not going to derive anything, just I just want to show you, that's all. Okay, so this is called convergent divergent nozzle. What is the Mach number? Less than 1 here. Mach is 1 and here Mach is greater than. So this is called supersonic nozzle. Okay, convergent and divergent nozzle. So and all the analysis you had seen, so no need to go for the again discussion and all about convergent nozzle and convergent divergent nozzle. I have taken 2-3 lectures for this in aerodynamics, compressible aerodynamics. So please go and watch that video. Okay, you will understand easily. It's very simple only. Fine, but always remember convergent divergent nozzle is what uh, uh, best suited for the supersonic. Actually, it is supersonic nozzle. Okay. Similarly, for convergent, only convergent nozzle, if you say, then it is best suited for the subsonic flow. and entry obviously inlet will be, it is subsonic, then inlet will be Mach less than 1, but at the exit what maximum Mach number is what possible, so we can say it is 1, not more than that. Okay, again if you want to accelerate the flow, so you have to add divergent section also, so it will become convergent and divergent, because this section is what, convergent. Okay, and this section is called divergent. Okay, this section. Okay, and this is the throat. All the discussion we already have seen, so not going in detail, otherwise it will take so much time here. Okay, so best I will, in short I will write, see, this portion is nothing but convergent, this this is nothing but divergent, and this is what constant called throat. Okay, throat, this is what constant is here. All right, so fine. Now what we are going to do here, the very important, uh, we need to write the efficiency, isentropic efficiency of nozzle first. First discussion is what, isentropic efficiency of nozzle, isentropic efficiency of nozzle. Okay, all right. So okay, so if you remind, this component was last component, so I must say 8 to 1 was diffuser, 1 to 2 was compressor, 2 to 3 was combustion chamber, 3 to 4 was turbine, and 4 to 5 is the nozzle. So this nozzle I can say 4 to 5, 4 to 5. Okay, 4 to 5. So this is the 0.5, or you just say 5 because it is going to exit from here. No need to write not. Not value will be used for the inner valve like compressor, combustion chamber, turbine, but nozzle is what going to exit to the atmosphere, so total quantity will not write, so I am writing here 0.5, and this part will be connected to the turbine, so this is the inner part, so I will say it is not 4, total value you will write for this. Okay, so whatever the pressure, temperature and pressure, temperature will be T naught 4, pressure will be T naught 4, temperature will be T5, and pressure will be P. Okay, this is the nozzle, and here this nozzle is what, obviously subsonic nozzle. All right, now so if you go for the isentropic efficiency, so isentropic efficiency of the nozzle will be denoted by eta n. Okay, it is denoted by eta n. All right, now what is the isentropic efficiency of the nozzle? So as I mentioned in diffuser, diffuser is what basically used to convert kinetic energy into pressure rise, so there will be the rise of enthalpy or rise of you can say temperature. So but turbine and nozzle both component will try to accelerate the flow, so in both cases there will be the fall of enthalpy or fall of the temperature. Okay, so first I will show you that TS slot, which is usually you have seen many books you have seen, and I have drawn when I had explained all the components. So there, all the uh, for the all the components I had drawn the TS plot. So here this is what T and this is what. So two pressure line you have to draw in TS plot. You know very well how to draw the this pressure line. So this will be the one pressure line and this will be the another pressure line. Okay, these are the pressure line. So obviously this not 4 value will be higher than whatever the value at 0.5. Why? Because not 4 is what connected to the turbine, and you know from starting only diffuser, then compressor, then combustion chamber, temperature and pressure will rise, but after turbine, combustion chamber, from the turbine to nozzle, all the pressure and temperature will fall. That is the functioning of the component. Okay, you have seen usually in previous lectures. So T naught 4 will be higher value. So I must say this is the P naught 4 line, pressure line, and this is the P5 pressure line. Okay, P5. All right, fine. So two pressure line I have drawn here. Now here you have in this plot, here you have to show the fall of the pressure and temperature. So how you would show? It will be similar like turbine, because in turbine also there was the fall of the temperature and pressure, and here also the same thing. So this fall, which is a straight line, which indicates isentropic fall, and this is the actual fall. Okay, I must say this is the phi dash, and this is the phi only, and this is nothing but not 4. Okay, this is nothing but not 4. All right, done. So and sometimes P5 is what pressure of atmosphere if it is fully choked. So and it is going to exit to the atmosphere, because here what we have, this is what atmosphere. Okay, so this pressure is nothing but PA, atmosphere. This is what atmosphere. Sometimes what is the pressure at 0.5, it is equal to atmospheric pressure. Sometimes it happens also. Okay, now so what is the isentropic efficiency of the nozzle? Eta n. Okay, now check the temperature. This temperature is nothing but at this point it is nothing but T naught 4. Okay, this will be T5 dash. Okay, T5 dash, and this temperature at this point, see here, this is nothing but only T5. So I must say, before writing the nozzle efficiency, check this T naught 4 minus T5. This is the actual fall of total temperature. And what is the T naught 4 minus T5 dash? It is isentropic fall of total temperature. Okay, this 2 point need to remember here. Now, what is the nozzle efficiency? So, nozzle efficiency is nothing but the actual enthalpy drop, actual drop divided by isentropic isentropic enthalpy drop. Okay, so how to write this? What is the actual enthalpy drop? See, actual enthalpy drop in terms of enthalpy you can write H naught 4 minus H 5. This is the enthalpy now divided by H naught 4 minus H 5 dash. Okay, so this eta nozzle you can write CPT naught 4 minus CPT 5 divided by CPT naught 4 minus CP 5 dash. If you solve this, then what will you get? P naught 4 minus P 5 divided by P naught 4 minus P 5 dash. This is what the nozzle efficiency. Okay, this is the nozzle efficiency. P naught 4 minus P 5 divided by this is the nozzle isentropic efficiency. All right. Now, the value of this nozzle efficiency, obviously it is depending on a wide varieties of factors such as length of jet pipe. Okay, and it is also depending on the frictional losses. If frictional losses will be more, then obviously efficiency will be less. Okay, it is also depending on the factor called swirl, because whatever the flow is coming from in turbine, it is coming in nozzle, it is coming from turbine, and in turbine obviously rotational flow will be there because it is a rotatory component. So it is called amount of swirl in the gases. Okay, available in turbine, so it will pass through the nozzle, so that swirling component will come. So that nozzle efficiency will also depend on the swirling velocity, that will also reduce the nozzle efficiency. So these are the factor depending for the nozzle efficiencies are length of jet pipe. Okay, one. Two is frictional losses. Three is the amount of swirl in the gases leaving the turbine. Okay, and because of these three reasons, that efficiency will have a lower value. Okay, if these losses are not there, then efficiency of the nozzle will be very high. Okay, so let me write the factors affecting factors factor affecting nozzle efficiency. Okay, so these are length of jet pipe, number two frictional losses in nozzle, number three swirl in the gases, leaving from turbine. Okay, otherwise the expected value for ideal cases, I mean if there is no losses, there is minimum swirl swirling available in the gases. So if assume that these losses are very less, so eta of nozzle, isentropic efficiency of nozzle approximate to 0.95. Okay, approximated. Okay, and we are considering these losses are very less, like the friction losses and swirling in the component, and due to length of jet pipe, uh, that is the optimum range, not beyond the range. If it is not beyond the range, then your nozzle will give the optimum efficiency, and it is approximate to 0.95. Sometimes if it is not given also, then obviously you take 100%, and if it is said solve for the real jet engine and solve and assume the appropriate value. So if it is real jet engine, so that time nozzle efficiency you need to assume, and what value you will assume that time, it will you will assume 0.95. So that value you should know. Okay, very nice. Now so there are two conditions for the nozzle, which is very important, and most of time these cases are, you know, uh, the affect the problems. I mean, importance of these two cases are unchoked and choked flow in the nozzles. So obviously there will be a nozzle loss for unchoked and choked flow. So we'll check what is the choked flow and what is the unchoked flow, and what is the condition for it. Okay, choked and unchoked condition, that we need to take care of it. So so now we'll go for the further analysis of this nozzle. So generally what happened actually, that conversion nozzles, I told you, it is for subsonic, hence conversion nozzles are used in almost all present subsonic transport aircraft. Moreover, in most cases, these conversion nozzles are also choked, and when it is choked, when Mach number reaches to 1 at the exit, and incomplete expansion of the flowing gases to the ambient pressure, okay, is encountered. At nozzle outlet, the gases exit at sonic speed while the pressure is greater than ambient pressure. Thus, a pressure thrust force is developed. On the contrary, a convergent divergent nozzle satisfied a full expansion to ambient pressure. That already we had discussed about the over expansion, under expansion, and a fully expansion case for the convergent divergent nozzle. So it doesn't mean only convergent divergent nozzle can be choked. No, it is wrong. Convergent nozzles also can be choked condition. Choked condition already we had seen in compressible aerodynamics. Choked condition is what? When somewhere in the nozzle Mach number reach to sonic flow is what reach to sonic velocity or sonic flow, and obviously at sonic condition Mach number will be 1. So somewhere in a nozzle, if Mach number reach to unit, means Mach is equal to 1, that condition will be called choked condition. Why? Because at Mach 1 the mass flow rate will be maximum. So as I have shown you, conversion nozzle also can have Mach is equal to 1. Maximum I have shown you here. See this diagram. See here I have shown you. So maximum Mach number at the exit is what possible, equal to 1. So this is the one condition when the nozzle, even though convergent nozzle will also choked condition. What about convergent divergent? If it is subsonic at the inlet in convergent and divergent nozzle, and at the exit of CD nozzle, if Mach is greater than 1, then it is 100% at the throat Mach is what? 1. Because at the inlet Mach is less than 1, at the exit of CD nozzle Mach is greater than 1, it is 100% sure at the throat Mach will be 1. Then only at the exit you got Mach greater than 1. That is the possibility. So that throat will have a choked condition, and whatever the mass flow rate now you will calculate, it will be maximum. That is the concept already we had seen in compressible aerodynamics. So in that detail I am not going to again waste my time, because you already have seen that. So you go and watch that recorded videos available, so you can have that discussion and knowledge. Okay, so that part I'm going to skip here, I'm not going into that. Now the next level I'm just going to tell you, when the nozzle is what choked and when it is unchoked, then what uh, calculation parameters will change for further calculation. Okay, calculation parameter in the sense what pressure and temperature you will take when it is choked condition, and what pressure and temperature you will take when it is unchoked condition, for the further calculation. Because as I told you, this nozzle is a very important component for the engine, because in the nozzle only the more and more expansion you will get. I mean, more and more expansion in the sense all the pressure energy available in the engine will be converted into kinetic energy. So you will have a optimum or highest exit velocity at the exit of nozzle, and if it is there, then obviously you will have a highest thrust or maximum thrust condition, you can say. Okay, so for this reason only, this choking and not choking condition we need to check. So here I have to write nozzle losses, or simply choked and unchoked condition for the nozzle. Choked and unchoked flow. Okay, and you have to see the condition. Okay, unchoked flow in nozzle. All right, fine. So previous, that TS plot you had seen for the nozzle, the same TS plot I am going to draw here. Which TS plot? See, this one is I have drawn this one here. Sorry. Uh, two pressure line here, this one. So this is the TS plot for the nozzle. The same TS plot I am just going to draw. Now I will show the velocity component and all. Okay. See. So two pressure line need to draw here. Node 4 and 5. So I must say this is what P5, okay, or this will also possible equal to atmospheric pressure. One more pressure line I will draw. P04 is okay. For P5 also need to draw. So because the station, if you check, it was not 4 and not 4 and 5. See, not 4 and 5. So P04 and P5. Where will be P05? If I, this P5 is what is static pressure at station 5. If I say what is the total pressure at station 5, then somewhere P05 will also come. So where will be the P05? Let me show you. So P05, this will be P05, okay, because whatever the pressure, P04 will be greater than P05, hence P05 line will be down only. Okay, now so check this TS plot properly. This is P5, okay. So this expansion, just say this is the point 5, okay, and this is the 5 dash. So this is P04, hence this line is, this point is nothing but 04, okay. Somewhere there will be P naught 5, so I can say this point is nothing but not 5. Okay, and here I can show this velocity component, how that P naught 5 you will achieve. So this is P naught 5 and this is P 5. How you will achieve that in terms of temperature? If I say, then it will be V 5 square divided by 2 Cp. I told you that last lecture how to write this. It's a total temperature. How? Check. This is T 5 dash. This is what T 5. This is T naught 5. Yes or no? Or let me give you accurate. It will be more clear to you. Okay. So this point will be, it is T naught 5 and obviously not 4 also coming, so T naught 4. In starting only, when I started explanation for the component, that time I said one thing, if you remember, diffuser and nozzle are non-rotatory component. In this component, we are not getting any work, we are not supplying any work, we are not adding any heat, we are not subtracting any heat from the diffuser and nozzle. Apart from nozzle and diffuser, check compressor, turbine and combustion chamber. In compressor, you are getting work from the turbine, means compressor is what extracting or absorbing work. So work is there. In combustion chamber, you are adding heat. Yes or no? You are burning fuel. In turbine, turbine is also rotatory component, so it is producing work. So that's the reason I am saying why temperature is constant. I am explaining here. So apart from nozzle and diffuser, all three components, compressor, combustion chamber and turbine. In compressor and turbine, work absorption and work extraction, work production is there. In combustion chamber, heat addition is there. But only nozzle and diffuser are two components which is stationary. There is no work absorption or consumption, there is no work production, there is no heat addition, there is no heat subtraction. So total temperature must be constant. Even though total pressure should also be constant, but because of the losses and all, we can say total pressure will not be constant. Okay, because of the losses practically. So for that reason, T naught 4 is equal to T naught 5, and the same thing you need to remember for diffuser, because this equation T naught 4 is equal to T naught 5, or in diffuser it was T naught A is equal to T naught 1. Very important. Sometimes in numerical, if you know T naught A, directly you can equate to T naught 1. In numerical, if you know T naught 4, then directly you can equate T naught 5. If you know this property. If you know it is equal or not, if it is equal, if you know, then directly in numerical you can use this. If you don't know, then there will be difficulties. You will have T naught 4. If you are finding T naught 5 or something you are writing, if you don't know it is equal, then it will be difficult to you to proceed the problems. Okay. Anyway, so this is the equation. All right. Now you understood total temperature. If you remember, total temperature is equal to what is static temperature plus velocity component divided by 2Cp. We already I had derived in compressible aerodynamics. So for that reason, see, this is what T5 to T5 to T naught 5. If you want to reach, then what component you need to add? You need to add velocity. What is the velocity? Because it is station 5, so it will be V5 square divided by 2. That's the reason I have written here. Hope you understand. All right. So this is the one TS plot. Okay, this is the one TS plot. This is one TS plot. In this TS plot, we have now P naught 4. We have now P naught 4. Okay, and we have this atmospheric value PA. Similarly, we have P04, okay, and one more value which is called PC. I will tell you how to get PC value. If this comparison, if you check, if this value is what, this relation, okay, if P04 by PA, okay, less than 2 P04 by PC, then one condition, this is the case 1. I will discuss this case, okay. This is case 1. This is case 1. Alright. Second plot will have, I will TS plot. The similar TS plot we have to draw here once again. So now hope you understood this plot, so I will go fast. Two pressure line, okay. This is what P04, this is what P5, okay. Now obviously somewhere P05 will be there just like here, so I can draw the P05 line here. So this is what I say, P05. So simple, here you can, as usual, just like a previous you had drawn. So these 2 points I am going to show you. This is phi, this is phi dash. So now, okay, so this is not 4 and this is what, not 5. To get this value, this velocity will be 5 square divided by 2. This is as usual. This is as usual. Okay. Fine. Now I am considering, because this point which is nothing but phi dash, so instead of phi we can write C, which is nothing but critical value. We can write C as a critical value, okay. So I can have this station phi, or better you just write instead of P phi, because this C phi and phi dash you have shown, so better you show this line as a critical value. So it will be easy to understand. So this is what critical value PC, okay. This is what point C, just like point 5, and this is what C dash. So if you say what is the C dash, it is nothing but isentropic critical value, okay. Now, so how to get the PC for isentropic flow? So it's simple only. Let me find the PC value for isentropic. So PC value for isentropic, it is PC dash or PC, because it is the same pressure line, huh? So for isentropic and real, temperature will change but pressure line will be same. See, C and C dash both are same. I mean temperature will be different, it is okay, but what about the pressure? It will be same. If you draw the pressure line, temperature line, so this is the TC, critical temperature, okay. This is the critical temperature. Now the point is how to get this PC value. So how to get this PC value? So it is very simple. What is the pressure line? P naught 4 by Pc, 1 plus gamma minus 1 by 2, okay, because this is the Pc, so I must write Pc, MC square, MC is the Mach number for the critical, MCR better, okay, to whole power gamma upon gamma minus 1. What is the Pc? It is the critical pressure at critical condition. What is the critical condition? It is already explained in compressible aerodynamics. Whenever the Mach number reaches to 1 somewhere in a flow field, then it will be defined as the critical. So if you, that time it was denoted P star value. So this P star is nothing but critical value. Okay. Hope you remind by P star, because P star we had used there. So this P star value will be critical value. Now here it is showing by PC. Okay. So nothing to confuse here. See. Now what is the P naught 4 by PC? 1 plus gamma minus 1 by 2. What is the MCR? It is 1 now. So whole power gamma upon gamma minus. If you solve this, then you will have a gamma plus 1 by 2 gamma upon gamma minus 1. Okay. Now, if I say what is the PC by, because I need to calculate PC value. So what is the PC by P naught 4? So PC by P naught 4 is nothing but 2 upon gamma plus 1 to whole power. What is the PC? This value you need to remember. This is very special, okay? PC is nothing but P naught 4 2 upon gamma plus 1 to whole power gamma minus 1. So this is the PC value. Okay? Alright, this is the PC value. Now, if you now compare, what comparison you have to do? If you are comparing case 1, what is the case 1? Case 1 is if you are writing P naught 4 divided by PC greater than P naught 4 by P5. This is case 1. Okay. What is the case 2? The case 2 is nothing but if P naught 4 by PC less than P naught 4 by P5. Okay, and you know P5 is the atmospheric value. Okay, so nothing uh, to be confused, because this P naught 4 by P5 itself is nothing but P naught 4 by P5 is what? PA. Okay, similarly here also I think if I will give this symbol, then there will be problem. Better you remove, and this is the equal value. Okay, this is the equal. Now there should not be confusion. Okay, because P5 is PA. So if P naught 4 by PC is less than P naught 4 by P5, what is the P5? It is again atmospheric. Okay, or we'll write this only. Whenever it is required, we'll write in terms of the atmospheric condition, they will mention properly. Okay, and similarly this condition also. Better. The condition will tell to you, okay? Here it is atmospheric condition, okay? See this, it is atmospheric condition, P5 is equal to PA, no doubt about it. But in any situation, if some in a statement, if they will change something, then you have accordingly you have to change. But actually, it is equal to atmospheric value. Okay, there should not be any kind of confusion. It is atmospheric value. Okay, right. So P naught 4 by Pc greater than P naught 4 by, instead of P5 Pa. Both I am writing. So whatever the given data that time you use that and compare. P naught 4 by AC. Okay. So these are the conditions for the choking and unchoking condition. So if this is happening, then it is called choked condition. Nozzle is unchoked condition. Then nozzle is unchoked condition. Okay, and this is happening. Nozzle is choked condition, where what is the PC? PC, I have told you, PC is nothing but critical pressure. I told you how to calculate this value. Here you have, no? This is the way to calculate this. You have to calculate this PC in this by this formula, and then need to compare this. If this is happening, then you must say it is the choke condition. Okay, all right, fine. Now we'll write the value of P naught 4 by P5 because you need to compare it. Okay, so how to get the P naught 4 by P5? Because you have to compare, right? P naught 4 by PC, here I have shown you, this is the way to calculate P naught 4 by PC. This is the way to write the ratio value of P naught 4 by PC, I mean in ratio. This is the ratio value P naught 4 by PC. But somewhere if it is required PC only, then you can use this relation. Okay. So P naught 4 by PC you have now. For choking and unchoking, you need to compare P naught 4 by PC with P naught 4 by P5. So now we'll go for the P naught 4 by P5 value. So both value will have P naught 4 by P5 and P naught 4 by PC. Okay. See, there should not any kind of confusion. P naught 4 by PC you have calculated by this way, this formula. PC you have now here also. Okay, so P naught 4 by PC now you have. To compare, to check the nozzle it is choked or unchoked, P naught 4 by PC you should have, and P naught 4 by P5 you have. You should have P naught 4 by PC you already have derived. P naught 4 by P5 we need to find. How we'll find? It is very simple only. See, we should write the formula for the nozzle efficiency, calculation of P naught 4 by P5 or P naught 4 by P. Okay. So how to get this? Check what formula we have based on that nozzle efficiency formula. What is the nozzle efficiency? Eta n is nothing but P naught 4 minus P5 divided by P naught 4 minus P5 dash. We already have written here. Check P naught 4 minus P5 divided by P naught 4 minus P5 dash. Now use this. Okay. Use this relation and we need to find this value. So what will be T naught 4 minus T5? So T naught 4 minus T5 will be what? Eta nozzle T naught 4 minus T5 dash. Okay. Now here anyhow we need to convert this because we want pressure P naught 4 by P5. So anyhow we need to convert this temperature into pressure, so we need to apply isentropic relation. How we can apply isentropic relation? It's very simple. The isentropic relation you can apply if you get this temperature in ratio. How to get this temperature in ratio? So you can write T naught 4 minus T5 is equal to eta nozzle efficiency, and you take common. What is the common here you are going to take? You just take common T naught 4. Okay. Then what you will have 1 minus T5 dash divided by T naught 4. Alright. Then what will be T naught 4 minus T5? It is nozzle efficiency. T naught 4 in bracket, what you can write? Check. You can write 1 minus T5 dash by T naught 4, or you can write T naught 4 T5 dash. You can write this. Then you can write eta nozzle T naught 4 in bracket 1 minus. What is this T naught 4 by T5 dash? This T naught 4 by T5 dash is nothing but it is 1 upon something. Yes or no? So you can say this is nothing but 1 minus T naught 4 by T5 dash will be T naught 4 by T5 the whole power gamma nothing by gamma. Yes or no? And this P naught 4 by P5 need to find anyhow. So you can say this is what T naught 4 minus P5 divided by eta n P naught 4 is equal to 1 minus 1 divided by P naught 4 by P5 gamma nothing by gamma to whole power. Okay. You need to solve this. Once you solve this, finally what you will get, two steps you have to do. Then P naught 4 by P5 will get here. Calculate, then you will get, and it is nothing but 1 upon 1 minus T naught 4 minus P5 divided by eta nozzle to whole power gamma upon gamma. This is the P naught 4 by P5. Okay. And there should not any kind of doubt here. If you check this T5 T04 also, you can change in terms of Mach number if it is required. Then how to do this? So one more step I will add here. Okay, check because this is also important. So this is the one formula. If all the temperature they have given, you can use this directly to get the result P04 by P5. And remember this P5 here, it is nothing but PA. Okay. Anyway, or you can write the same. I'm just going to one more step need to write here. Check the previous P04 by P5. It is nothing but take the whole bracket as it is 1 upon 1 minus 1 minus, take this T04 both places it is available. So if you take common of T04 by eta nozzle, so what you will get? Check eta nozzle, and obviously T04 also available in denominator. So what you will get in bracket, it is 1 minus T5 by T04. The whole bracket is gamma upon gamma minus 1. See this T04 cancel out. So what you will get? P04 by P5 is equal to, you will have 1 divided by 1 minus 1 upon eta nozzle in bracket 1 minus T5 divided by T04 to whole power gamma upon gamma. Okay. Now by the relation only you had seen T04 and T05 was same. Check. I explained that time only. T04 is equal to T05. Yes. So whatever the T04 we have here, whatever the T04 we have here in this equation, see this T04 is nothing but T05. So you can say T5 by T05, or can write here T04 by T5, or T04 you can write T5. So this will be what? 1 plus gamma minus 1 by 2, because it is at station 5, so I can write station 5 gamma upon gamma minus. So this formula we can use. Sorry, this is temperature, so not required. Sorry. No? This formula we can use now. Where you need to put? You need to put at this T5 by T04, because this T04 become T05. So T5 by T05, or you can say in denominator you take T05 by T5. So this T05 by T5 value will be like this. Final result I am going to write. What is the P04 by P5? P04 by P5. Check this result. This P04 by P5 I am going to write. So this value you can write 1 upon. This formula is very important. Okay. 1 minus 1 upon eta nozzle. Check eta nozzle in bracket 1 minus, it is T 1 minus T5 by T04, or you can say 1 upon T04 by T5, and T04 is nothing but T05. So T05 value is this. So I can write 1 upon. Now it becomes T05 by T5, and T05 by T5 value is this. So what you can write? 1 plus okay. Done. This is the result to check the nozzle is choked or not. If nozzle is choked at the exit is what? Station 5. So for exit condition, what will be the M5? M5 will be M5 will be 1. And if M5 is what? 1, then no doubt you may able to get the P04 by a PC also. And what value of P04 by PC you may get if nozzle efficiency is given. Here whatever the P04 by PC you have written, see, this is also P04 by PC, this one. But in this case the nozzle efficiency is not given. If nozzle efficiency is not given, then this result you can use. But if the nozzle efficiency also they have given, then how to get P04 by PC? That is the difficulty. Okay, so that time if nozzle efficiency is given, then P04 by P5 you have calculated. This is the P04 by P5. This result you got. Okay, this result you got, you save it. You can save this result you got now. Okay, this is the result for P04 by P5 calculation. But I am saying again, I want to write P04 by PC. So P04 by PC, this result you have seen, it will work, no doubt. It will work, this P04 by PC, but it will work when the efficiency, nozzle efficiency is not given. But if nozzle efficiency is given, then P04 by PC, this formula will not work. So that time what you will do? So will simply P04 by PC you can get in this formula only. Instead of M5 you just make 1. So I can write to get P04 by PC from P04 by P5 if nozzle efficiency given, then what you will do, that M5 at the exit should be 1 because you are going to write PC. PC means critical value. So M5 is equal to 1, then it will achieve critical condition. So this P04 by P5 becomes now P04 by PC. Yes or no? If it becomes P04 by PC, then what will be the formulation here? Nothing. Simple. Instead of M5 you just make 1 and again you write the result. So directly I am going to write it is 1 upon 1 okay, 1 minus 1 by nozzle efficiency inside check. This is 1 minus, and this is what 1 plus gamma minus 1 by 2 because M5 become 1. So it will be 1 plus gamma minus 1 by 2. So it will be gamma plus 1 by 2, and then it will reverse. So 2 upon gamma plus 1 and 1 minus will be there. So I can write 1 minus 2 upon gamma plus 1. The whole power is check gamma upon gamma. So this is the P04 by PC in terms of nozzle efficiency. Okay, this is also very important. I told you P04 by PC both cases. If nozzle efficiency is not given, then I have shown you previous that formulation. Okay, but if nozzle efficiency is given, then this formula will be used. How to get P04 by P5? This is the formula. Okay, P04 by P5 or P04 by PA. This is the formula. Now, what is the mean of it? The meaning is very clear. If the nozzle is unchoked, okay, if the nozzle is unchoked, always remember when you are writing P04 by PC, okay, the same equation you have seen for P04 by P5. This is the master formula Okay, from this equation you can write P naught 4 by P5 and P naught 4 by PC, and that two you have to compare. Okay, so P naught 4 by P5 you have to get value by this formula. Again, if you want to write P naught 4 by PC, then what you will do? Simply PC means what? Critical condition. Critical condition means flow achieves sonic velocity. Mach becomes 1. So instead of M5, you just make 1. To write this P naught 4 by P5, to write this P naught 4 by PC, you just make M5 is equal to 1. So if I write M5 is equal to 1, then P5 will be now PC. So only the P naught 4 by PC becomes this. Again, if you solve one more step, I think if you 1 minus 2 upon gamma plus 1, so it will be gamma plus 1 minus 2 divided by gamma plus 1. So I think gamma minus 1 divided by gamma plus 1, something you may get. Okay. So you can write this P naught 4 by PC. Check what result finally you will get 1 upon 1 minus eta nozzle. One more step you solve 1 plus this, take gamma plus 1 minus 2. So it is gamma minus 1 by gamma plus 1. It is gamma minus 1 by this result we need to remember. The whole power is now gamma upon gamma. So this was little bit lengthy, but one time we have done all the steps. So for you, if you solve the problem, then for you it will be very easy to solve. Okay. If you directly mug up the formula, so it will give the difficulties because you don't know what value came from where. So now you from starting to till end you have done one time at least. So you will able to know, okay, this is steps coming from this condition. Okay, so that is the one thing. So now you understood when flow will be choked, when flow will not be choked, that mathematical condition I have given. And physical meaning of choking also I told you. Choking means maximum mass flow rate and Mach reach to sonic condition means Mach is equal to 1. That is the physical meaning of the choking condition. And mathematical condition also you have seen that relation P naught 4 by P5 and P naught 4 by PC, that relation you have seen. But now the story is what not ended here. What is the main story? Now the main story is what? The from choking and unchoked condition, you need to write the velocity so that you can get the thrust. That is the main motive actually. So now the conclusion part I am going to write here. So what is the conclusion? Conclusion. Conclusion for case 1. Okay, I say case 1, if nozzle is unchoked, if nozzle is unchoked, okay, if on nozzle is what unchoked means, that condition you need to remember, this is this should be on your tip. Okay, if nozzle is what unchoked, that means P naught 4 by PC greater than P naught 4 by P. This is the condition when the nozzle is what unchoked. So conclusion part I am going to do. First case I have taken from the conclusion part. If the nozzle is what unchoked, take P naught, take P naught 4 by P5. Okay, for further calculation. For the further calculation, and we have optimum expansion. Okay, so for unchoked nozzle, unchoked nozzle, the exit or jet velocity can be calculated by this formula 2 cp t naught 4 minus t pi t naught 4. This will be the jet velocity when the nozzle is what? Unchoked condition. When the nozzle is what? Unchoked condition. So this will be the jet velocity 2 cp t naught 4 minus c5. How to check nozzle is choked or not? By the formula p naught 4 by pc. If it is greater than p naught 4 by p5, then you say nozzle is unchoked, then you write exit velocity by this formula and go for the calculation of thrust. That's the reason it is given for further calculation. Further calculation means what? For the calculation of thrust. So what jet velocity you will write? You will write v is equal to 2 cp t naught 4 minus t5. Alright, now second case 2. So if everything you forget, no problem, but this conclusion you need to remember, okay? And that final formula p naught 4 by pc and p naught 4 by p5. Forget everything, derivation and all. The fourth thing you need to remember, okay? Case 2. What is the case 2? If the nozzle is choked, okay? What is the choked condition? Just opposite p naught 4 by is less than p naught 4 by p5. If the nozzle is choked, then obviously critical condition will come. So if nozzle is choked, then p naught 4 by pc take for further calculation, okay? For choked nozzle, exit or jet velocity can be calculated by v is equal to 2 cp t naught 4 minus pc. Check this. Now this is what case 1, which is unchoked. This is the choked condition. So station will be C. This was unchoked, so 5. So P naught 4 by P5 or P naught 4 by PA value you will take for further calculation. And this is the case when P naught 4 by PA greater than by P naught 4 by PC. So this is the choked condition or choked of nozzle. Okay, this is the unchoked condition. So if it is choked condition, then C quantity you have to take. Means at this value you have to take critical value. If it is unchoked, then station 5 value, whatever the pressure at station 5, whatever the velocity, what is the Mach number at 5, what is the temperature at 5, that value you have to take. I mean T5 you will take for the velocity. But if it is choked, then what value you have to take? You have to take TC. Because now it is choked, so critical value you will have. Alright, hope you understood. So that's the reason in this formula. See what is the difference in the velocity. The difference is only phi and c. See, if it was unchoked, so we have taken t phi here. If it is choked, then we have taken, instead of t phi, we have taken tc. That is the only difference. Okay, that is the only difference. All right, simple. Or if you solve this also, then you may get gamma RTC. Technically also you can think, what is the Mach number? M is V by A. So for choked condition, critical Mach number will be 1, and this is exit velocity, this is the speed of sound. So what is the mean? Exit velocity is the speed of sound, which is nothing but gamma RTC. In this way also you can understand. Okay, so this is the final actually. So what points you need to remember? Many things I have explained here, because this is the, like, thoroughly I have given. Important point is what I will tell you. Important point, you need to understand this. If possible, you need to understand this TS plot, when nozzle will be choked, when it will be unchoked. Number one. Number two, this P04 by PC value you should know. When nozzle efficiency is not given, then this formula will be P04 by PC. Okay. Nozzle efficiency, obviously it is common thing, you know. This is the P04 by P5, or this is the final value of P04 by P5. This one you need to remember. This is the main. Okay, important. This formula you need to remember. Somewhere you write each and every component. Now you understood. So directly formula also if you mark up, it is okay. But without any derivation, without single time derivation, if you go formula and direct mark up, then you will have a trouble. But now one time you have derived it, you have seen the all steps. Now if you mark up the formula, it is okay for you. So this is P04 by P5 and this is P04 by PC. These two very important to remember. Okay, and it is very easy. Only P04 by P5 you remember. For P04 by PC, you just make M5 is equal to 1. So this will be the P04 by PC as a same thing. This is the formula you need to remember for your exam. Exit velocity for both condition, choked and unchoked, you should remember. And case 1 and case 2. So the last is what? How to get TC. Okay, how to get TC value. TC is the critical temperature. How to get it? It is very simple. What is the formula of T04 by TC? See, T04 by TC, or T04 by, you just say T5 better. T04 by T5. So what will be the T04 by T5? It is 1 plus gamma minus 1 by 2 into M5. If I say T5 is equal to TC, choked condition, then what will be M5? It is 1. So what will be T04 by TC? It is nothing but gamma plus 1 by 2. So what is TC? TC is nothing but T04 done. So now you have TC, right? You have TC. Once you get TC, then directly root of gamma RTC you have to now you have TC. So for the choked nozzle, root take gamma RTC root value, then you will have exit velocity. Once you have exit velocity, then you go for the calculation of thrust. Done. So this was the whole analysis for the nozzle. Okay. Not a single thing I have missed. Whatever the possible things or possible contents required for your GATE exam or any one day exam, PSU exam. So each and every points I have considered here. Not a single things I have missed. Okay. One time in your examination they have asked related to the efficiency problem in GATE. They had asked. Okay. They had given the efficiency of diffuser, efficiency of compressor, efficiency of turbine, combustor and nozzle, and they said compare it. Okay, so that value you need to write. This is the approximated value. Okay, that also need to write here. This nozzle is what done. So final. All the components I have discussed. This is the final discussion going to start from the engine components. So the engine performance is estimated. The engine performance is estimated, okay, estimated by defining the adiabatic efficiencies as follows. So I am going to give one: diffuser, compressor, combustion chamber, combustor, okay, which is also called burner sometimes, and turbine, hood, and nozzle. So approximate value I am going to give for it, okay. So diffuser efficiency it is less than 0.9 and greater than 0.7. Why it is varying? I told you when I explained diffuser, I said diffuser efficiency is what is strongly dependent on flight Mach number. So for that reason, this variation you are getting 0.7 to 0.9. Compressor efficiency, second number. Compressor efficiency is less than 0.9, but it is greater than 0.85. Approximate value I am saying. Now coming to combustion chamber efficiency. Combustion chamber is also called combustor, also called burner also sometimes. So it is equal to or less than 0.99 and greater than or equal to 0.97. Turbine efficiency eta T, turbine efficiency less than 0.95, 0.9. Last, nozzle efficiency less than 0.98 and greater than. So this is approximated value, okay. One time in examination they had asked this comparison, so you can now compare this value, okay. All right, done.